When we talk about states of matter, another term we might use is phases of matter. They mean the same basic thing: states of matter, phases of matter. And there are 4 states of matter. So I'm sure you're familiar with solids and gases. What's the 4th state of matter that often we might not talk a lot about? Jonathan? Plasma. And we'll talk in a minute about what a plasma is, but it is another state of matter in addition to solids, liquids, and gases. All right, so we're going to talk just a brief overview about each of them, then we're going to get into some more details and talk a little bit about changes from one state to another. So first off, solids. We're all familiar with solids, and I have a cube of metal here. Okay, it's obviously a solid. And solids, the atoms or molecules that make up that solid, they're in a regular arrangement, a regular pattern. They're orderly. So that's what they may look like if you're imagining the atoms of a solid. And we know that solids have definite shape. So this cube has a certain shape. It also has a certain volume. I can measure its size and multiply and find the volume of that cube. And also it's difficult for other molecules to penetrate into a solid. Liquids when you imagine what their molecules are, how they're arranged, they're not in a regular pattern, not very orderly alignment. And we know that liquids, do they have a definite shape? No, they take the shape of whatever container they're in. So if you take some water, you could pour it into a tall, skinny glass, and that's the shape that it takes. Or you could pour it into a wide, flat container. That's the shape it takes. So shape will conform to the container that it's put in. But it does have a definite volume. So if I take my tall, skinny container of water and measure the volume, and it's 100 milliliters, and then I pour that 100 milliliters in a flat pan, it's still the same volume of water, regardless of the shape of the container that it's in. And then we have the gases. And the molecules in the gases are not arranged in any orderly pattern. They're moving all over the place. They're not really attracted to each other in any way, so they're sort of all spread out and moving in random ways. And gases have neither definite shape nor definite volume. They also take the shape of their container, but they also expand to fill the volume of whatever container that they're placed in. And then we have our 4th state of matter, plasma. And plasma is, I think, sometimes a little bit hard to visualize because it's not something we have a whole lot of direct experience with. But a plasma is often called an ionized gas. And what that means is the atoms of the element, the electrons have been sort of stripped off and separated from the actual atoms. And so what you're left with is a bunch of nuclei surrounded by a bunch of sort of randomly placed electrons. Often, plasma comes from a super hot ionized gas. It can be found throughout the universe. It's actually the most common state of matter in the universe, even though we don't experience it a whole lot. It's found in stars, and the sun is mostly plasma. Sparks, lightning bolts, the aurora borealis. Those are examples of plasma. If you've heard of the solar wind, okay, that is plasma. Also, you ever have seen in the store one of those globes with a small globe inside and the beams of light coming off that you put your hand on and all the beams? That's plasma inside of there. That's gases, neon, argon, gases like that, that are in a, when electricity is added, they form a plasma which glows, making those patterns. If you look at sort of a color version of the periodic table, often what you'll see is the symbols are in different colors, sometimes blue, red, green. And those colors indicate sort of the typical state that that element is found in at Earth. For example, oxygen is typically a gas on Earth at normal temperatures. And calcium is a solid, okay? And mercury is a liquid. Now, they can be changed. You can change matter from one state to another by adding or removing heat. But most substances have a typical state of matter at room temperature. So let's talk a little bit about these changes. So how do we change from one state of matter to another? And this is some stuff I know you guys talked about in elementary school. Physical versus chemical changes. So a physical change in matter. So how could you describe it? What is a physical change? Chloe? Kind of. People will often say that, and it's not. But what about this? Can I reverse this?
No.
If I have a shattered piece of glass,
It's called super glue.
I can't really reverse it. Okay? If I tear up a sheet of paper, can I reverse that?
Yes.
Not really. So that's often not the best way, although it's kind of correct. There's other ways to say it. Jonathan?
A change that does not change the state of the matter.
No, not the state. It could change the state of the matter. Emma?
A change in the physical appearance of...
No. Morgan?
Where the chemical makeup of it stays the same.
Yes, you're not creating any new substance. The chemical formula, it's the same material. So when I shatter a glass like this, it's still glass. I haven't changed any new substance. If I take an ice cube and melt it, the state has changed. It doesn't have the same properties anymore. It's now a liquid, but it's still water. It's still H2O. Even if I take some salt and sprinkle it into water and dissolve it, that's not a chemical change. The salt is still salt. The water is still water. I still have the same substances. I've just changed them in certain ways. But it's the same stuff. So if you're not creating any new type of matter, that is a physical change. How is that different from a chemical change? Cool?
A chemical change changes the appearance and state.
state of matter are physical changes. Melting, evaporating, freezing, those are always physical changes.
I don't know how to explain it, but it's like if you burn a piece of paper.
That's an example.
Yeah.
Because what have you done when you burn a piece of paper?
You put a chemical reaction, a chemical change.
Yeah, but I'm asking, what is a chemical change?
It's a different substance.
It's a different substance. It's not the same stuff anymore. So if you burn paper, the molecules that made up the original piece of paper are changed. We've created carbon dioxide in the water and carbon monoxide and the ash that's left over. Those are all new substances that weren't present before. If you leave a piece of iron out exposed to oxygen, it's going to oxidize, it's going to rust. That rust is actually a new compound that's forming. That's a chemical change. And we often can recognize a chemical change by looking for certain things. So some of those things, if heat is being released, I add two liquids together and all of a sudden it starts to get hotter. It's an exothermic reaction. That's a chemical reaction. Chemical change taking place. Sometimes gases are released and a substance bubbles. That's often a sign of a chemical change. Sometimes a solid forms out of two liquids of a precipitate. Thank you. So this is how we know often that a chemical reaction is taking place. Can we go back there? So if we think about some examples, fireworks exploding, metal rusting, cooking things. Cooking is a chemical reaction. The actual molecules change. Fruit rotting, anything burning, toast burning. Okay, that is a chemical reaction. The leaves of a tree changing color in the fall. Those are chemical changes. And in a chemical change also, we know that there's no loss of mass, no gain of mass because of the law of conservation. But you kind of have a change in volume sometimes. They won't because new chlorophyll is produced.
Is the bottom center one with the fruits, is that just like fruits rotting?
Yes, it's rotting fruits. Florian?
Like, if you burn something, how is there no loss of mass if it, like, holds up and gets smaller?
Because, if you take a piece of paper and you burn it, okay? So if I take the paper, I measure its mass, I burn a piece of paper and I have the ash left over and I take the mass, it is going to be different. But did I lose mass? Where is the missing mass? It's in the air, it's the smoke, the water, so that mass is still a part of it, so it's the same amount. All right. So we have a few slides here where we're just going to compare solid, liquids, and gases in some of their basic properties. So if we were like to sketch out maybe what the molecules arrangement is, in a solid, they're all sort of regularly spaced and very close together. In a liquid, they're not in an orderly arrangement. There's a little bit more space. And in a gas, there's more space and more, they're in a more random location. So just give a general sketch there. It doesn't have to be. We also have some terms we use to talk about solids, liquids, and gases. Okay, we say that solids are frozen. Yes, it is. Just a term we can use for something as a solid. Liquids we call fluid. It's another word for a gas. No, air is a specific mixture of gases. A vapor. About shapes, we already talked about this. About solids, Autumn has a definite shape. Liquids, Bianca?
It takes a shape.
Yeah, no definite shape. It takes the shape of its container. And the same is true of gases. About the movement of the molecules within each state of matter. How are the molecules of a solid moving? Ashley? Very little. They're sort of vibrating. Okay, so they're not sort of moving from place to place, but they're sort of vibrating in place. So what do you think about a liquid? How are the molecules moving in a liquid? Cole?
A little more, but they're kind of like not as much as that.
Yeah, they're moving more. They're actually trading places with each other, sort of staying connected somewhat, but they are moving around with more freedom. And in gases, the molecules are moving very quickly and constantly in motion. Okay, the freedom that the molecules have. How much freedom is there for the molecules in a solid, Emma?
Little to none.
Yeah, very little freedom. Basically, the molecules stay in place. Liquids are in between. They move around, like you said, trade places, but still sort of stay together. And in the gas, there's complete freedom. Molecules can move wherever they go. Compressibility is how much can you compact the atoms within that solid. Solids, it's almost impossible to compress a solid because they're already sort of tightly packed together. It's also very difficult to compact a liquid because molecules are still pretty close together. They have more freedom of movement. They're still pretty tightly packed. Gases, however, are easy to compact. They can be compressed down to a great degree.
Is that density higher?
Yep. Yep. Densities. If you compress those molecules, density gets higher. So density, solids, very compact. They have the highest density. Liquids are in between, and gases are generally the least dense. Now you should remember that water is an exception, that in water the solid form is less dense than the liquid form. That's unique about water. Bless you. Bless you. The volume tell me about the volume of a solid. Yeah? Definite. Liquids? Grant? Definite. Gases? Olivia? Not definite. Gases expand and they fill whatever container that they're placed in. Okay, last slide of this. So the bonds between molecules, the sort of connection, it's greatest in what? Emma? Solids. Liquids have very weak, loose bonding between atoms, and gases have basically none. Think about the amount of energy they contain. Which state of matter contains the most energy? Jonathan? Yeah, gases do. Solids have the least energy. There's the least movement of molecules. But they're in between. Now this sort of goes along with the bonding between the molecules, but the amount of attraction between molecules, greatest in what? And least in?
Yeah.
Yes. And then finally, how about the effects of heat? What happens when you heat a solid? Eventually this happens. Nicholas? True. What else? Morgan?
It melts eventually.
Yeah, eventually it turns into a liquid. What happens when you heat a liquid? Joey?
Turns into vapor.
Yeah, it turns into a gas. Vapor. What about when you heat up a gas? Basically the temperature just increases. And it can eventually form a plasma, but really the temperature just increases. There's no next state. Our last topic is to talk about the changes of state and what happens and what happens to temperature in these situations. So we know if we are adding heat to something and it turns from a solid to a liquid, what's the term we use? Melting. Or if we have heat and we change a liquid to a gas, there's a few words we can use here. What? Evaporate, vaporize. Sometimes we say boil, although usually we're talking about water. Vaporization, probably the most one that's used scientifically most. When we remove heat and a gas changes into a liquid, what's the term for that? Joey?
Condensation.
Yeah, condensation. Liquid to solid? Bianca? Freezing or solidification. And then there are some instances when a material will go directly from solid to gas or gas to solid. And we have a special term for that. Does anyone know what it is?
I know what I just.
It's called sublimation. Sublimation. And it can be called that going the opposite way as well, or it could be called deposition if it's going to gas and solid, but we could say sublimation. Now let's say I'm looking at a graph. You're going to be doing a fair amount of graphing over the next few days. So I have a graph here with time on the x-axis, temperature on the y-axis. So what am I doing to this substance? Cool? I'm heating it up. So if I start with a solid down here, so it's increasing in temperature. But then it gets to a point as I continue adding heat where the temperature stops changing. Say this were a piece of ice that we're at negative 10 degrees Celsius to begin. And I start heating it up. And the temperature goes from -10, -9, keeps going. What temperature do you think it flattens out? Joey?
0.
At 0. What starts happening at 0 degrees? Nicholas? It starts melting. And while it's in that process of melting, its temperature stops changing. It doesn't continue to get warmer. The temperature stays at the melting point, which for water is 0 degrees, until when? It'll stay at that temperature for a while, until what happens? Grant? Until it's a completely a liquid. So all of the solid is gone, and then it's a completely a liquid. And then, as I add heat, the temperature starts increasing again. And it continues increasing until I get to, if this is water, what temperature would this be? What? It's a science class.
100 Celsius.
100 degrees Celsius. And what would we call? What's happening when it gets to 100? Its temperature stops changing for a while. What do we call that? How? Yeah, vaporization. And then if I continue adding heat, after it's completely vaporized, what am I left with, Olivia? A gas. And the reason that graph levels off there is because as you're adding the heat to, let's say, the ice, the heat going in is not increasing the speed of the molecules. It's going to separate the molecules and move them out of position to change the solid water into liquid water. The same is true if I go in the opposite direction. I remove heat. If I start with a gas, it cools down until it does what? Bianca?
Condensation.
Yeah, condenses, condensation. And then after it's fully condensed, what state is it in? A liquid. And we continue cooling it down. And then eventually what happens to that liquid? Zachary? Yeah, it freezes. Until it's in what state of matter? Olivia? A solid. This is what it looks like in both directions. Solid, melt, liquid, oil, gas. And the other way, all right, good job, Ted. It's a lot of notes for on there.